Let's look at another block diagram. Rockets take in propellant and use energy to produce a high-speed exhaust. Conservation of momentum between the exhaust and the rocket produces thrust. Make sure you understand this diagram because we're going to expand it in the next slide. Now, this is the same diagram but with more detail. Follow along as we go through the steps. We can break the process a rocket uses to produce thrust into two steps seen in this figure. First, energy must be transferred to the propellant in some form. Second, the energized propellant must convert to high-speed exhaust. In other words, energy first transfers to the incoming mass. This high-energy mass then converts to high-speed mass, producing thrust. Going back to our balloon rocket, we note that the propellant is air molecules that are energized by the elastic balloon skin. With the energy from the balloon, the air molecules are accelerated through the stem or nozzle. There are only two basic types of rockets in use today. How we classify them depends on the form of energy transferred to the propellant and converted to high-speed exhaust. The first type is a thermodynamic rocket, which relies on thermodynamic energy or heat and pressure. And the second type is an electrodynamic rocket, which relies on electrodynamic energy or electric charge and electric or magnetic fields. For today's discussion, we're going to focus on thermodynamic rockets. Your text has information on electrodynamic rockets for your review. Thermodynamic energy is in the form of heat and pressure. A covered pot of water like this tea kettle on the stove reaches high temperature and produces high pressure steam. Most of us have seen how the thermodynamic energy in steam drives trains or produces electricity in power plants. By the way, you may notice this particular tea kettle has little rockets on the top which turn around as the kettle heats up and the thermodynamic energy pushes them along. In a thermodynamic rocket, thermodynamic energy transfers to the propellant in the form of heat and pressure. A propellant can produce heat through a chemical reaction or from external sources such as electrical, solar, or nuclear energy. Propellants in gas or liquid form are delivered to the rocket under pressure. With both heat and pressure present in the combustion chamber, many particles are excited and accelerate through a nozzle to create high-speed exhaust particles. Here is an image of the European Space Agency's Smart 1 spacecraft, which demonstrates solar electric propulsion. This method uses the sun's energy to power an electric propulsion system, which is an example of an electrodynamic rocket. By far, the most commonly used types of rockets rely on nozzles. Nozzles convert the thermal energy produced by chemical, nuclear, or electrical sources into kinetic energy through thermodynamic expansion. You can see the Saturn V's main engine nozzle that helped propel astronauts to the moon. Hot gases produced from burning propellants in the combustion chamber move into a narrow section of the nozzle called the throat. Past the throat, the exhaust expands until it exits the nozzle. Nozzles can convert the thermal energy of the hot gases in the combustion chamber into the kinetic energy of the exhaust, which is exactly what we need to exchange momentum with the rocket and create thrust. A standard thermodynamic rocket has two main parts: a combustion chamber, where energy transfers to a propellant, and the nozzle, where the high-energy combustion products convert to high-velocity exhaust. Now, we're going to talk about the Bernoulli principle discovered by the Swiss scientist Daniel Bernoulli in the 18th century. The Bernoulli principle tells us that low-velocity gases move into the nozzle's converging section, which is one that's getting smaller and smaller, called the throat of the nozzle. As the liquid and gas go through the throat, it goes faster and faster until it reaches the speed of sound at the throat's narrowest part. At this point, we have very high-speed, low-mass particles that exchange momentum with the rocket body. Rocket engines are also called reaction engines because they operate on Newton's third law of motion. You remember, for every action, there is an equal and opposite reaction. Because the Bernoulli principle is one of the most important concepts in science, let's go over it again as we follow this diagram. The Bernoulli principle tells us that low-velocity gases move into the nozzle's converging section called the throat. They go faster and faster until they reach the speed of sound at the narrowest part of the throat. As the gases expand past the throat where the nozzle increases in area, the velocity keeps increasing to supersonic speeds. The high-speed exhaust produces thrust. Not all nozzles are created equal. In the ideal case, we'd like the pressure of the exhaust coming out of the nozzle to equal the pressure of the outside atmosphere. But let's think about what happens when exit pressure doesn't equal the pressure of the outside atmosphere. When this happens, we have a rocket that's not as efficient as it could be. Here are the gigantic nozzles of the Saturn V moonflight rocket at Cape Canaveral, Florida in 1991. Okay, let's see where we are with the nozzles. We have the ideal situation where the exit pressure equals the pressure of the atmosphere, as shown in the top diagram. This produced the most efficient rocket thrust. But we just said that that doesn't always happen. In some cases, we get either an overexpanded or an underexpanded nozzle. At the top here, we can see the ideally expanded nozzle, where the pressure at the exit equals the pressure of the atmosphere. Notice how the exhaust is coming straight out of the nozzle. The overexpanded nozzle occurs when the exit pressure is less than the pressure of the outside atmosphere. You can see where the flow separation point, the small space between the orange exhaust and the nozzle, sends shock waves that can destabilize the rocket. This can occur during liftoff because many launch pads are near sea level, where the maximum level of atmospheric pressure can cause shock waves to form at the nozzle's lip. These shock waves rob kinetic energy from the flow. That lowers the exhaust velocity, decreasing the overall thrust. The lower diagram with the underexpanded nozzle shows the case where the exit pressure is greater than the pressure of the outside atmosphere. Here, the orange-colored exhaust is going well outside the nozzle. What do you think might happen to the rocket in this situation? That's right, the flow is underexpanded, so not all available heat and pressure converts to velocity. Obviously, the expansion ratio of a rocket is an important problem to solve. We don't want a rocket nozzle that's over or underexpanded. We want a nozzle that's just right. The total expansion in the nozzle depends on its design. We define the nozzle's expansion ratio as the ratio between the nozzle's exit area and the throat area. Here you can see the exhaust from the two Titan IV strap-ons. At this point, do you think the nozzles are underexpanded or overexpanded? Right, the nozzles are underexpanded, and you can see that the exhaust goes well outside the boundary of the nozzle from left to right. It turns out that a thermodynamic rocket's efficiency depends on only two things: the temperature in the combustion chamber and the molecular mass of the propellants. The higher the temperature in the combustion chamber, the more efficient the rocket. Molecular mass is a measure of the mass per molecule of propellant, and we try to use propellants that have very low molecular mass. So to improve the efficiency or specific impulse of thermodynamic rockets, we try to produce the highest combustion temperature while keeping the propellant's molecular mass as low as possible. For this reason, hydrogen is often the fuel of choice because it has the lowest possible molecular mass and burns at high temperatures. This is an important concept, so let's restate it. The efficiency or specific impulse of a thermodynamic rocket increases as the combustion temperature increases or as the molecular mass of propellant decreases. This diagram is an expanded view of a thermodynamic rocket system. It's a summary of all the material in this lesson so far, so pay special attention as we go through the steps. We can see the various inputs, process, and outputs of a thermodynamic rocket. Propellant and energy combine in the combustion chamber to produce high-temperature combustion products. The nozzle converts these high-temperature products to high-velocity exhaust. The nozzle performance depends on its expansion ratio and the outside atmospheric pressure. The final output is high-speed flow that produces thrust. Total thrust depends on the mass flow rate, or mdot, and the exhaust velocity. Now that we've filled your head with the behavior of gases, or blown a lot of hot air depending on how you look at it, let's put all these principles together by looking at an example of the simplest type of thermodynamic rocket in use. A cold gas rocket uses thermodynamic energy in the form of pressurized propellant as its energy source. It's similar to the toy balloon we talked about earlier. Although spacecraft designers don't send balloons into orbit, the basic principles of the cold gas rockets aren't that different. This is a typical small rocket or thruster shown in a cross-sectional drawing. The gas enters from the right and stays behind the seal until it opens on command, releasing the gas through the nozzle. A coiled spring stores mechanical energy that can be converted to work. An example is an old-fashioned wind-up watch. Any fluid under pressure has stored mechanical energy that can be used to do work. Any rocket system containing fluids under pressure uses this mechanical energy in some way. For cold gas rockets, this is the propellant's main energy. Cold gas rockets are very reliable and can be turned on and off repeatedly. This produces very small, finely controlled thrust pulses called impulse bits. A good example of an application of a cold gas rocket is the Manned Maneuvering Unit, or MMU, which uses compressed nitrogen and many small thrusters to give astronauts complete freedom to maneuver. Cold gas systems are very useful for human spaceflight because they're very safe. As a final summary of the basic principles and propellants used by cold gas rockets, take a look at this table. Make sure your idea of the cold gas rocket's principles matches this table. If it doesn't, you should go back over the last few slides and the material in your text. Answer the questions on this slide. Even focusing on the thermodynamic rockets gave us a lot of material. Make sure you understand the concepts and information. If you feel confident, you may want to study the rest of the text, which deals with electrodynamic rockets. If you're uncertain about the activity question answers, check with the text again or ask your teacher. Like the previous material, this information is important because it sets the stage for future work. In this brief clip, you'll see the launch sequence of one of our country's most recent expendable rockets. Note each event and try to understand how each event helps us get spacecraft into orbit.
Ten, 9, 8, scissor start, 6, 5, 4, 3, 2, 1, 0, plus 1, liftoff, 2,
of the first flight of the Delta IV Heavy rocket,
5,
launching a near Air partnership in
7,
space access
8,
between the United States Air Force
plus
and Boeing.
10, 11, 12, 13, 14, 15.
Okay, partial thrust and level on all vehicles. Chamber pressure is dropping on the port and starboard as expected. And we can see a positive indication of a successful strap-on separation. Okay, partial thrust level has been commanded into the core vehicle as we prepare for staging. Okay, booster solid rocket motor ignition has been passed. As for K12 step. NEDS deploy indicator, email is unlocked. Igniter.
We have had stage separation, and the second stage is powered up.
Okay, we have fairing.
We have successful fairing separation.
Running on the second stage.
This lesson introduced important concepts for how rockets work, thrust and how impulse and velocity change affect a rocket's design. It also described thermodynamic rocket technologies. And we saw some great photos of rockets, which I hope got you more interested in rockets and all their possibilities in our world today. In the next section, we'll look at mission management from the team and management point of view.